Hi everyone. In this video, we're going to look at the rules from section A in a couple different contexts. The good news is I have no fresh rules for you today or tomorrow. So, first off, you can take more than one derivative of a function. So like here, instead of y, why don't we just call this f of x for consistency? If we have some function, f of x equals all this stuff, we can take its derivative. This would tell us the slope of the original function everywhere. Let's see, to do that, this would just be a whole bunch of power rule. And I'm going to show my work. As you get better and better, you don't necessarily need to show all your work on these parts or on this style of problem. Whoops, I did this one backwards. That's because I was trying to rush through in my head. And then you can take the derivative of a function's derivative. And this would just be called either the second derivative or the double derivative. And if you're curious, well, it's quite literally the slope of the first derivative. Or another way you could describe it is, how is the derivative changing? How is the slope of the original function changing? Whoa, that was weird. Okay, I don't know why this keeps happening. I'm going to full screen, so maybe that won't do it. So our second derivative here, we would just use the exact same rules. So power rule a couple times here. How about 30x minus 14? And we could keep going. We could find the third derivative, which again is how the second derivative is changing. The only thing here would be the 30. And finally, the fourth derivative, which at this point, formal notation actually stops using the tick marks at 3. Typically, you would put a number in parentheses. The parentheses show that it's not like squared or something. This would read the fourth derivative of x would be 0. It's very hard to describe what the third and fourth derivatives and any subsequent derivatives are of a general function. But again, the easiest thing you could do for right now is just know that each one is describing how the previous one is changing. We'll get into some more applications of multiple derivatives later on in the chapter. In fact, I think we've got, nope, we don't have them for a couple sections. Oh well. Okay, second problem. Find any horizontal tangents for the function y equals this stuff. So horizontal tangents, that's what my eye is drawn to. The slope of a horizontal line is 0. So what I'm going to do first is find the derivative, and then I'm going to set it equal to 0. So let's do that. Since the function was named y here, you could either use y prime or you could use f prime of x like we did before. It doesn't matter. Again, we'll have two power rules here. So 3 times 5 is 15. Subtract 1 from the exponent. And 6 times 5 is 30. Subtract 1 from the exponent. And then our job is to figure out where is it horizontal. So again, I'm going to now set that equal to 0 and solve. If this was a calculator problem, just graph it, find the x-intercepts. I did set up this problem so it could be solved without a calculator because I don't want you to forget algebra entirely. Something that I noticed right away is that 30 is a multiple of 15, and I could also maybe factor out an x squared from each term. So how about let's factor this. Let's say this is really 15x squared times 1 minus 2x squared equals 0. And this will lead us to a couple solutions. Because now we have a product equal to 0, we can set each part equal to 0. So we can say 15x squared equals 0, or 1 minus 2x squared equals 0. This one, divide by 15, take the square root. The 0 is going to stay. And now for this one, how about let's add over the 2x squared. Divide off the 2. And then take the square root of both sides. Don't forget, because you took the square root, there are two solutions, a positive one and a negative one. This is where the horizontal tangents occur. if you wanted to actually find those tangent lines yourself, all you would have to do is then plug these x values back into the original y equals equation, and that would give you where they occur. So for example, this one would give you the horizontal line y equals 0, and this one would be, well, there'd be two of them, and I don't want to think about cubing 1 over the square root of 2 right now. You certainly can do it, but it's of no major concern to us. Okay, example 3 is a bunch of application of derivatives. Surprise, surprise, that's what the whole video is about. But the context is a little bit different. So see how the problems are presented using the traditional notation of u's and v's. And what we've done is we've given you just a bunch of information about those functions at specific points without actually telling you the functions themselves. So we've given you both of the function values at 0 as well as their derivatives at 0. And our job is to come up with a, b, c, and d, all these weird things, which we can totally do. So in problem A, it says find the derivative of u times v. Well, that's a product, so let's use the product rule to figure this out. Now, we remember the product rule as dfg plus f times dg. So now let's see. In this case, since the problem is written with u's and v's, you could just quickly rename them to be f and g. So how about df would be the derivative of u, since that one came first, times g, which in this case is v, so I'm going to leave it the same, plus, and then f, so u, whoops, that was weird, u times the derivative of g, which in this case is v prime. And then all of this is at 0. So I'm just going to say I'm going to evaluate this statement at x equals 0. That's what the vertical line means. I'm going to evaluate this, and then writing something below tells the reader, hey, this is how I'm evaluating it. Which would be -3 times -1 plus 5 times 2, which comes out to 13. Yes, it comes out to 13. I don't know if I said this in the previous video, but if you forget the order, oh, is it DFG or is it FDG first? It doesn't matter because they're added. So do it whichever way you remember. In part B, now we have u divided by v. So again, our rule for quotients was low times d high minus high times d low, strike a line, square below. So in this case, it'd be low, so v, times derivative of high, so u prime, minus high, so u, times derivative of low, that'd be v prime, strike a line, square what's below. So I'm going to take this. Again, I'm going to evaluate it at x is 0. So let's see, that'd be -1 times -3 minus 5 times 2 over -1 squared, which +3 minus 10 over 1, -7. Now for part C, it's a quotient rule, but just the variables are flipped. So now the v is in the numerator, the u is in the denominator. So let's work through that one real quick. So low d high minus high d low, strike a line, square below. Fun fact, it was math class that made me start putting the tails on my u's. Before I would just do these. And as you can tell, if that's a u and that's a v, oh boy, stuff gets hard to tell the difference between. Anyway, okay, so let's, whoops, probably should say where I'm evaluating that. I'm evaluating that at x is 0. So then, let's see, it's basically like the one above, just flipping the stuff around. 5 times 2 minus -1 times -3. I always put the parentheses around the thing so I make sure I don't get confused with that minus. And then divided by 5 squared. So 10 minus 3, so 7 over 20. Okay, finally, let's see for this last one. Oof, I ran out of space. Sorry, guys. Here, we'll just squeeze it down here at the bottom. We've got an easy one, and then we got a product rule. So remember, the constant multiple rule is the 3 just comes along for the ride, and then you take the derivative of the function u. So the first part's already done, easy. For the second part, we have a product rule. I suggest you think of this as being 2 parentheses u times v. That way, it's just easier when you're taking the derivative. Just put a big old set of parentheses around your work with the product rule. So let's see. df g plus f dg. And then I'll go ahead and, well, why distribute when we could just multiply later? Okay, so we got, let's see, 3 times negative 3 plus 2 times. Oh no, I did all that in my head, in my notebook. Well, hey, up above we said that's 13, right? Yeah, in part A we said that was 13. So negative 9 plus 26, 17. Cool. Let's turn the page. Okay, so we've done tangent lines and normal lines a little bit in the past. Just keeping this problem in here to make sure you stay fresh on all that. So our task in example 4 is find an equation of the line perpendicular to the tangent to the curve. Here's the equation at the point. Okay, so we need the equation of the line perpendicular. We need a normal line. But first, we have to come up with at least the slope of the tangent line. Then we'll make it perpendicular. So there's our original function. We need its derivative so we can come up with its slope at that point. Power rule here, so 3 times 2x minus 7 times 1 x to 0. Again, you don't necessarily have to go through all that as you're becoming more and more proficient with all this. And then it's at this point, so let's plug in x equals 1 to figure out the slope there. So let's evaluate that at x is 1. That would be 6 times 1 minus 7, so negative 1. Okay, so the regular slope, so how about the tangent line slope, is negative 1. The normal line, or the perpendicular line, is always the opposite reciprocal. Well, the opposite will flip this to positive 1, and the reciprocal of 1 is still 1. That's not so bad. So let's point slope form it up. Slope is 1, and then let's just stick the point in there. You don't even have to write the slope because it was 1, I guess. I guess you could have just said x minus 1 minus 2 or y equals x minus 3. I'd take these both. Doesn't matter. Okay, our last one here is where we're tasked with finding where the slope is a specific number. In this case, it's a slope of 4. We've done this a little bit in the past. I know we've solved for where horizontal lines are a lot, so that's where the slope is 0. Functionally, this is not going to be any different other than that we're changing the number that we're going to set the derivative equal to. But since we want to know where is the slope something, we're still going to have to start by finding the derivative. We'll have to find the equation that tells us the slope. So you're going to have to use the power rule twice. So there's our derivative. Now our job is figuring out where is it 4. So let's solve. So subtract the 1, and then divide by 3, and then take the square root of both sides. So at x is either positive or negative 1, the original function is going to have a slope of 4. There's a follow-up question here. It says, at what value of x does the curve have the smallest slope? So basically, let's just call this part B. I know I didn't label it that way, but when is slope, and smallest, can we just say minimized? Minimized. Well, our equation for slope was 3x squared plus 1. So let's think about that for a second. What would that function look like? Are you thinking? It's a quadratic. It's got a +1. It's not got any shift left or right. It's got a vertical stretch of 3. So it would probably look something like this. And if I was going to label the graph, I'd say it's a graph of y prime. So because it's a quadratic, it definitely has a defined minimum at the vertex. That vertex there is 0, 1. The y value is 1. That tells us because the minimum of the derivative is 1, the smallest or lowest slope of the original function y is 1. Hey, that wasn't so bad. See you guys tomorrow.